There's a world of small parts constantly working in near perfect order to keep all life alive. That's a pretty scary statement if we think about it. It's also why it's important to know how those small parts work. The world is changing, and it's often within those small bits that we find solutions. Last video, we talked about the organization of the periodic table and saw that elements could be separated into metals, nonmetals, and metalloids. Metals and nonmetals are opposites of each other, which means that everything a metal is, a nonmetal is not, hence the name. Metals have characteristics like being hard, shiny, ductile, malleable, and good conductors of electricity. Nonmetals have the opposite of those characteristics, meaning that they're often soft or a gas, they can't be bent into shape or wired, and they are not good conductors of electricity. Okay, so what about metalloids then? In fact, they have a mix of both characteristics. And they're really important when it comes to things like our electronics, primarily because metalloids are known as semiconductors, and semiconductors are found everywhere and almost in every single electronic that you could imagine. Aside from physical properties, metals and metalloids also differ in their chemical characteristics. These chemical properties are mostly based off of their number of valence electrons. Quick little question quiz. What is a valence electron? If you chose C, you would be correct. So like we discussed in the last video, metals are found in the lower group numbers. And a group number also can tell you the number of valence electrons that we're working with. An atom's ideal number of valence electrons would be 8. They want no more and no less. It follows the idea of too much of a good thing can also be a bad thing. Like if you were to eat 1, 2, 3 donuts, that's a good number. That's a happy number. But triple or quadruple that, and you would be found on the ground probably holding your stomach. So back to the atoms. Atoms that are found in groups 1 and 2 will have 1 and 2 valence electrons respectively. And because these atoms are so far away from their goal of 8 total valence electrons, their chemical characteristics makes it easy for them to give away those extra electrons. For example, let's say we have a sodium atom. Naturally, this atom has 1 valence electron hanging out in its outermost energy level. Take that away, and the next energy level becomes a complete 8 valence electrons, making this atom extremely happy. After the electron is gone, the atom now has an imbalance of protons and electrons. Instead of the normal 11 protons and 11 electrons, this sodium atom now has 10 electrons, meaning that it has more protons than electrons. Like we've discussed in previous videos, protons are positively charged. So when we're looking at the periodic table, we assume everything to be neutral. But in this case, now that we have 1 more proton than electron, our atom is now going to be considered an ion. Specifically, this atom is going to have an overall +1 charge. We would rewrite the element symbol using a plus to indicate that this has happened. When an atom has changed its charge to become more positive, we call this new transformation a cation. Easy way to remember this is literally by thinking of cats because cations are positive. Atoms found in later groups like group 16, 17, 18, they have valence electrons 6, 7, and 8 respectively. For these later groups, we just remove the 1, and that will tell you the number of valence electrons. However, keep in mind that this only works for groups 13 and onwards. Our transition metals don't follow rules, so we kind of omit them from this. But because these later groups now have a higher number of valence electrons that make them closer to that happy number of 8, they are going to want to receive or take electrons to get them to that goal. This balance of give and take from metals and nonmetals creates an amazing back and forth that helps to prevent atoms from becoming too chaotic. Let's look at an example of fluorine. Naturally, fluorine has 7 valence electrons hanging out in the outermost energy level. That is so close to 8. By accepting an electron that is either being donated or shared, this fills the energy level to a full 8, and the fluorine atom is happy. This again creates an imbalance of protons and electrons, but this time it's because we have 1 extra electron. And like before, this means we're going to have to rewrite the symbol. Except because we have one extra electron, this is going to be a negative charge. So we're going to write a minus next to the symbol, again, indicating that this has become negative. Whether it's positive or negative, anytime an atom has a charge, it can be called an ion. Specifically, though, if it has a negative charge, it's going to be called an anion. Sorry, I don't have an easy way to remember anion. Just remember cations are positive, and then the other one is the anion. But later, we'll discuss how these cations and anions work together to form different types of bonds. Anyway, happy sciencing, and I will see you next time. Bye!